All right, kids. We got chapter 3, another episode of Stats with Glenn. This is the special St. Patrick's Day edition. Thus, I'm wearing, as you can see, my green shirt. I've got my green pants on, in case you're wondering. Is he also wearing green pants? The answer is yes. And look at this 4-leaf clover / broccoli entity that I've made here, just for you to celebrate St. Patrick's Day. DNA testing recently revealed that I am actually approximately 7% Irish. Big surprise of my family, by the way. Grandma Sadie. Who knew? Great-grandma Sadie. Anyways, here we go, kids. We are going to go into chapter 3. And I know I say this about a lot of the chapters in this book, but I swear this might be my favorite chapter. Standardized scores. I will tell you that this course is incredibly cumulative. Everything builds on everything else. And so one of the last things we learned about was variability, standard deviation, and the mean. And that stuff's all going to come into play with standardized scores, or what we also call z-scores. And you will see that z-scores end up being the basis for almost everything in the upcoming chapters. It's a very foundational concept in statistics. So what z-scores or standardized scores allow us to do is it allows us to think about a score. So a z-score allows us to conceptualize a score, or conceptualize a raw score, in a standardized way. Regardless of the scale that the score comes from. So regardless of the scale that the score comes from. Should I stick with this green, or do you think I've done enough green?
Enough green.
I think I've done enough green. Kids, I'm going to go to the standard black. But again, remember, it is 2020. This is St. Patrick's Day. So z-scores allow us to conceptualize a raw score in a standardized way, regardless of what scale it comes from. So imagine this scenario. E.g., remember E.g. is a Latinism meaning for example. Imagine you take your SAT and you take your ACT. And imagine your score on the SAT is 1200, and imagine your score on the ACT is 29. And you're trying to figure out which one should I send to schools when I'm applying for college. Well, on one hand, 1200 is a lot higher than 29, right? So just in an absolute sense, simply naively, you might think, well, look at my SAT score. That's way more than my ACT score. But of course, we know this is on one scale and this is on another scale. What the z-score process allows us to do is to think about these scores in a standardized way, regardless of scale. So suppose, I'm going to put up means and standard deviation. These might not be actual norms, but they'll be close enough or useful for us to think about. Imagine for the SAT, the mean is 1,000, and the standard deviation is 200. And imagine for the ACT, the mean is 25, and the standard deviation is 4. Okay, and then in a little bit, we're going to go into the real nitty-gritty details about how we actually calculate and compute all this stuff. But right now, I'm just going to have this as what I call given information. So at this point, we can take our two raw scores, right? A raw score is like an actual score as it naturally comes out. So we can take our 1200 and we can compare it with our 29 by putting them on the same scale. That's kind of the beauty of z-scores. That's like the first way I like students to think about what is a z-score and how is it beneficial. So here's a formula for z-score. As I like to tell my students, with 0 exceptions, every formula we use in this class is conceptually meaningful. And I never want a student to just know a formula, start putting numbers in, and have no idea what he or she is actually doing. You should always know what the formula is all about. The most conceptually useful formula for the entire semester is this, for my money. Z equals x minus m divided by standard deviation. Seriously, I love that formula. What it's telling you is that a particular z-score equals your particular raw score of interest minus the mean from the relevant scale, divided by or taking into account. So divided by kind of means relative to or taking into account the amount that scores vary from the mean on that particular scale. So this means exactly what it is. We can interpret a z-score as follows. It is essentially the number of standard deviations above or below the mean that a particular raw score is. So this is probably written almost exactly as it's written in the textbook, by the way. The number of standard deviations above or below the mean that a particular raw score is. Thus, a z-score can be thought of is a comment on a raw score. So that's what a z-score is. A z-score is a comment on a raw score. It is this specific comment. It is saying where is that raw score relative to the mean of the distribution that it came from in light of the standard deviation of the distribution that it came from. So now we can compute the z-score corresponding to each of these raw scores, and we can essentially see, given that they come from different scales, which one's higher. And if I were a student and I computed all this, I would probably send whichever one was higher as a z-score to universities. So let's use this simple formula to figure it out. Hate to do it, kids, but I'm going to erase my four-leaf clover for this purpose. Okay. So if x equals 1200, right? So this is the SAT data. Z equals the particular raw score of interest, which is 1200, minus the relevant mean, which is 1000, divided by the relevant standard deviation, which is 200, which equals 200 over 200, which equals 1. 1.0. What does Z mean? It is the number of standard deviations above or below the mean that a particular raw score is. So this particular raw score of 1200 is 1 standard deviation above the mean. So anytime you ever get a z-score, it can always and should always be thought about in terms of what it means conceptually. So when you get a positive z-score, that means that your raw score is above the mean. If you get a negative z-score, and we'll do examples of that pretty soon, you're going to get a raw score, a z-score that is negative inside. So the SAT is pretty good. This person did 1 full standard deviation above the mean on the SATs. Not bad. Now, given the information we have for the ACT, let's see how this person did on the ACT relative to the scaling of the ACT. X equals 29. Z equals the particular raw score of interest, 29, minus the mean, which is 25. Oh, look what happened. You see what happened?
Yeah.
Oh man, this is interesting. Okay, divided by 4, which is the standard deviation, which equals 4 over 4. Kids, by chance alone, it's the luck of the Irish, an amazing coincidence. Both of those raw scores, given the data that I gave you about the scales, correspond to a z-score of 1. So based on the information I gave you, the raw score of 1200 is 1 standard deviation above the mean for the SAT scores. The raw score of 29 is 1 standard deviation above the mean for the ACT scores. If I were a student and I were applying to colleges, would I worry about whether I send the SAT or the ACT in this context? I would not, because what the z-scores tell you is they're equivalent in terms of how good they are relative to the scales they came from. That was totally by chance, kids. Look at that. That's a St. Patrick's Day benefit right there. Okay, so let's get some data. The way that this all comes about, and I'm going to work through this at least one time in full so that you have a sense of how this connects with what we did in Chapter 2. In Chapter 2, we started with some raw scores. Okay? I'm going to give you raw scores. I'm going to make up 4 people, and I'm going to make up GPAs for these 4 people. The first guy, I'm going to name James. The second guy, I'm going to name Sal. And the next guy, I'm going to call Brian. And the final guy, I'm going to call Joe. And yes, my favorite TV show is Impractical Jokers, and these are the guys from the show. And I happen to know quite a bit about these guys. Do you know that James graduated from Georgetown University? Think about that. These guys all went to college. I believe Brian did not graduate, but anyways, they're obviously brilliant. So, I'm going to give you GPAs for these guys. So I'm going to give James a 98. This is high school GPAs. I'm going to give Sal a 90. I'm going to give Brian an 80. And I'm going to give poor Joe a 65. He's smart, but maybe not academically. Okay. Now imagine we wanted to get the z-score for each of these individuals. So we know their raw scores, and we know where they are relative to one another, but what the z-score will tell us is where each of these particular raw scores is relative to the mean of this sample. So to get the z-scores, remember z equals x minus m divided by standard deviation. So we're going to do that 4 times, 1 for each joker. We're going to take each of these raw scores, subtract out the mean, which we'll compute in a second, and divide by the standard deviation. Okay, and again, I'm doing this just to show you the details. This will be the only time I do it, but for this chapter, but to show you the details of how we actually come about and create this information. So we're going to subtract out the mean. There's my handy calculator. We got 98 plus 90 plus 80 plus 65, 333 divided by 4. And Dana, if you want to check my work at any point, that's not a bad idea. And the mean is 83.25. And if you're watching the video and playing along at home, I will tell you this, 2 pieces of information that I swear you'll find useful, even if you find this arbitrary. One is every single step I put up here, even if it seems redundant, unnecessary, do it, because I've been teaching this stuff since 1996, and any step I put up there is not superfluous, even if it seems like it might be. Students I've seen that, let's say I have 6 columns in a problem, and students that I've seen put up like 4 columns or organize it differently, not gonna work out. Use the same process that I use. I promise you that there's reasons for each step. The other thing is the APA, or the American Psychological Association guidelines on rounding, is round everything to 2 decimal places. And so that's another thing that's gonna be beneficial, especially if we're trying to arrive at the same answers if we use the same rounding rules. rules, that's going to be beneficial. And chapter 2 has a little section all about rounding processes if you need to review that. So there's x minus m. Remember, here's x minus m as its own column. And you might recall from chapter 2, this is called the deviation score. Deviation score corresponds to how much each particular raw score deviates from the mean. So we got 98 minus 83.25, which is 14.75. 90 minus 83.25, which is 6.75. 80 minus 83.25 is going to be negative 3.25. And 65 minus 83.25 is negative 18.25. Remember, that column should sum to 0, so if you want to check your work, you can do that. I'm eyeballing it, and it looks like it's going to sum to 0, so that should not be a problem. The next thing we do is we need to get rid of those negative signs. And so now we're going to take all the numbers and we're going to put them in another world. We're going to put them in the world of squared numbers. We're doing this for a practical reason. We're doing that to kill these negative signs, because any index of variance or variability needs to be a positive number, because there's no such thing as negative variability. So this is squared deviation scores. X minus m squared. 14.75 times 14.75 is 217.56. 6.75 times 6.75 is 45.56. 3.25 squared is 10.56. And 18.25 squared is 333.06. Okay, once we get our squared deviation scores, you remember we're moving toward standard deviation. We will now come up with 3 overall indices of variability, and each one feeds into the next one, with the final one, or the third one, being standard deviation. Standard deviation is not only the most conceptually useful, it's roughly the average amount that scores vary from the mean, but standard deviation also is in the z-score formula, so we need the standard deviation. Okay, so the first overall index of variability is going to be the sum of the squared deviation scores, which is simply the sum of that column. Nothing complicated, nothing fancy. It looks like a fancy Greek set of symbols. It's just adding those numbers. So 217.56 plus 45.56 plus 10.56 plus 333.06 is 606.74. You get the same thing there? Okay.
Good.
So it's accurate. Okay, so after I get my sum of the squared deviation scores, you remember there's a problem with that because that's in the world of squared numbers. It's not comparable at all to the scale that we started in. It also doesn't take into account the number of scores that we have, so it's kind of just a number without much meaning right here. So the next thing we're going to do is SD squared. SD squared is essentially, it's the variance, and it is essentially the average of the sum of the squared deviation scores. So sigma x minus m squared divided by n, which is 606.74 divided by 4. Which my calculator is saying 151.69. Okay, 151.69. Now you remember, That is still in the world of squared numbers. That's why we have this squared here. It's not on the scale that these numbers are on, remember, because these are on non-squared. Remember, we squared it along the way. We haven't undone that yet. We need the standard deviation. So the standard deviation is the square root of SD squared, is the square root of 151.69, which equals 12.72. So, there's the end of the rainbow for you kids. 12.72, that is our standard deviation. Standard deviation is roughly the average amount that the scores vary from the mean in this sample. It looks like the scores vary a good bit. You remember the range here is 65 all the way to 98. So there's a pretty high standard deviation, meaning that their GPAs are kind of all over the place, right? So you remember standard deviation is an index of how much the scores vary from one another. And the answer here is they vary quite a bit from one another. We're now going to compute 4 z-scores. Let's take a look at James Murray's z-score right here. Okay, so z equals x minus m. So x is 98. Here we actually have a column which is x minus m. So 98 minus the mean of 83.25 is 14.75. Divided by the standard deviation, divided by?
I think that's wrong. The standard deviation. I think it's a 12.3 something.
Wait.
Unless my calculator's in the wrong.
Wait, 151.69. Hold on, kids. Dana's usually right. Let me just check this. I got 12.32.
Yeah.
Points for Dana, associate producer and director, by the way. Thank you, Dana. 12.32. That was a little St. Patrick's Day joke on my part, kids. So the standard deviation is 12.32. I was close. So okay, so here's the first z-score. Remember, what is z? It is a comment on the raw score. So it's a comment on James's raw score. James's raw score is 98. The z-score, once we compute it, will tell us about James's raw score. It's saying how far above or below the mean is James's raw score. So it's x minus m, which is 14.75 divided by the standard deviation, which, as Dana tells us, is 12.32. So that is 1.20. Only round to 2 decimal places. 1.20. Okay, what I like to do, I'm not going to do this right now, even though I'm tempted to, but at this point in class, what I'll usually do is I'll ask a student to explain what that means to my mom in Florida. How can you explain this to the layperson in your life who hasn't taken stats, who doesn't really get this, but you need to explain it? And in the middle of class, my students know I have no problem calling my mom on speakerphone when she's in Florida. We're not going to do that now, kids, but could you explain what this means to my mom in Florida? Remember, it is a comment on James's score, James's raw score. His raw score is 98. So what this z-score means is that his raw score of 98 is better than average, better than the mean, and not only that, but it's a lot better than the mean. Okay, that's kind of the level at which my mom would get it. It is. Then you could even say it's 1.2 standard deviations above the mean. My mom would probably not like that, but you could probably say it's a lot better than the mean. And you remember, James Murray went to Georgetown University. So next we're going to compute Sal's z-score. So remember the z-score, there's a z-score corresponding to each particular raw score. Z is 90 minus the mean, which is 6.75, divided by 12.32, which is 0.55. Okay, so what do we know about that z-score? We know that it's positive. If you have a positive z-score, based on how this is calculated, you know that the raw score is above the mean. And the fact that it's 0.55 standard deviations above the mean means it's a bit above the mean, but it's not super above the mean like James's score is. It's not as far from the mean as James's score is. So it's above the mean, but closer to the mean compared with James's score. Okay, let's take a look at Brian over here. Brian's raw score is 80. The mean, or the average, is 83.25. Right away, even if you didn't know anything about stats or z-scores or this or that, if you were Brian's mom, what would you say to Brian? You'd probably say, Brian, you're not doing as well as everybody else, right? Your score is below average. Z-scores think this way, okay? So that is going to correspond to a negative z-score. When the raw score is below the mean, z-score tells you that in terms of it being a negative z-score. So let's take a look. The deviation score is negative 3.25, divided by the standard deviation of 12.32, which is negative 0.26. Is Brian in big trouble? No, he's not in big trouble, but he's below the mean, and he's kind of close to the mean. We know that because his GPA is, or his z-score is negative 0.26. That means that it is 0.26 standard deviations below the mean. It's a little bit below the mean, but it's not like the worst ever. The worst ever is Joe over here. So let's take a look at poor Joe Gattos. He's got a raw score of 65. The mean is 83.25. His raw score is much less than is the average. That's going to correspond to a z-score that's negative and somehow indicative of it being not so good. So let's take a look. Z equals the raw score minus the mean, negative 18.25, divided by standard deviation of 12.32 equals negative 1.48. Okay, so this z of negative 1.48, what that's telling you is, remember, every z is a comment on the raw score to which it corresponds. So it is a comment on Joe's raw score of 65. His raw score of 65 is 1.48 standard deviations below the mean. That guy's got to get to work. That's what I'm going to say. Okay, I'm going to add a new joker. I'm going to put, the new joker's name is Andrew. And Andrew's score is 83.25. I'm using this as a very targeted example. Okay, Andrew's score is 83.25. That's not by coincidence. What is that? That's exactly the mean. Okay, think about what a z-score is. Z corresponds to how many standard deviations above the mean or below the mean a particular raw score is. This particular raw score is exactly the mean. It is 0 standard deviations above the mean or below the mean. Z for Andrew is 83.25 minus 83.25, right? So it's x minus m. This is x, the mean is 83.25, divided by the standard deviation of 12.32 equals 0. So if you have a z that equals 0, that means that the raw score that it corresponds to is exactly at the mean, which I think is a useful piece of information, a useful way to think about things. Okay, so this is z-scores. This is why they're so useful. This is why they're so powerful. They're very interpretable, and they're the basis of everything else we're going to do. They're the basis of correlation, which is the next chapter, which is the basis of regression, hypothesis testing. This stuff's all going to come back. There's one additional thing regarding z-scores that I want to get into. We can convert a z-score to a raw score. Okay, so far we've done examples where we take a raw score and we convert that to a z-score. We can go the other way. We can take a z-score and figure out what a raw score is. Okay, so for that last example, the mean Is that what I had? I think
Yeah.
that's what I had. And the standard deviation was 12.32. Okay, so now I'm gonna make another joker. This other joker's name is Megan. And what we know about Megan is that her z-score equals, I'm gonna put 1.6. Now, if you know someone's z-score, what do you do? If I were gonna explain how strong Megan was academically to someone, if I were gonna call my mom in Florida and explain, hey, here's how Megan's doing academically, would I want to do that in terms of z-scores? No, because my mom would say, I don't know what you're talking about, right? So I would need to convert that to a raw score. And you'll see throughout the rest of the course, there's a lot of times when you need to convert a z-score to a raw score for all kinds of reasons. Now you remember, z equals x minus m divided by standard deviation. So if we need to convert that to a raw score, this is just a splash of algebra, nothing killer, splash of algebra. We want to solve for x. Okay, so in other words, if we have all that information, we want to be able to figure out x. So if we move this around algebraically, we multiply both sides by standard deviation, so z times standard deviation. We can add the mean to both sides, so plus the mean. And so this is the formula. This is just an algebraic reconfiguration of this z formula that is used to turn a z-score into a raw score. So that's all it is. So now, if we know that Megan's z-score is 1.6, how can we figure out what raw score that would correspond to? So let's take a look. X, or the raw score, would equal that z-score, 1.6, times the standard deviation of 12.32, plus the mean of 83.25, 1.6 times 12.32, which is 19.71, plus 83.25. That actually equals, look at this, kids, 103. It's off the scale. Wow, what a score. So the score is actually 102.96. So it's actually off the scale. Sometimes z-scores don't know what scale you're on and don't really care. So you'll see there's a couple times when z's kind of overshoot or undershoot from what a scale actually might be. So this is z-scores. Z-scores are really conceptually useful. Each z-score is a comment on a raw score. It tells you where that raw score is compared to the mean, taking standard deviation into account. It is the basis of lots of statistics that are coming up in future modules. We can also take a z-score and turn that into a raw score, which is something we'll be doing in future modules as well. And that is Chapter 3, Stats with Glenn.